Safina ma'am,
Yes, sir.
please.
So, yeah. A warm good afternoon to one and all. I now call upon Dr. Jackson to deliver the welcome address. Sir, please.
A very good afternoon to one and all present here in both Google Meet and also in the YouTube live link. So it's my pleasure to welcome you all to the fifth day of this faculty development program organized by our PG and Research Department of Mathematics, V.O.Chidambaram College. So first, I welcome today's resource person, a man of simplicity, Dr. K. Nagarajan, former head and Department of Mathematics, SRNM College, Satur. A hearty welcome to you, sir. And also, I welcome our department HOD, Dr. A. Nagarajan, and also our faculty members. Welcome you, sir. Also, I welcome today's participants. So, participants, without you, this program won't be a grand success. So, I welcome you all to this fifth day faculty development program. I may now call upon our HOD, Dr. A. Nagarajan, to give a short introduction about today's resource person. Please, sir.
My friend Dr. Nagarajan sir and my dear department colleagues and all participants. I introduce our friend Dr. K. Nagarajan. He has completed MSc degree and MPhil PGDCA and PhD and he is head and associate professor in the Department of Mathematics in Sri SRNM College, Satur. And also he has also served in professor and head in Kalasalingam University years, and his total experience is 37 years. And for in MPhil, 12 years service in MPhil. His area of specialization is graph theory, and his research experience is more than 15 years. And number of MPhil scholars guided is 41, and the number of PhD scholars produced is 9. Number of papers published is 100. Number of seminar conference attended is around 50. Number of seminar conferences acted as a resource person around 10, and the number of webinar acted as a resource person is around 5. And the number of seminar conducted is 6 as conveners. Number of paper presented is 4, and number of journals acted as a reviewer is 7. And he has also undergone a project, a UGC minor research project, and also board of studies member. And during his service, he is a dean of academic affairs. With this introduction, I hand over the session to Jackson.
Thank you, sir. So, now I request the resource person, Dr. K. Nagarajan, to deliver his lecture. Please, sir.
Thank you very much, sir. Good evening to everybody. First, I thank the authorities of V.O.C. College, and I thank also the head of the department, Dr. A. Nagarajan, who is also my guide. And I thank the Dr. Jackson for organizing this webinar. And I also welcome the department members of V.O.C. College. And I welcome all the participants. First, I thank you very much for all participants to hear this webinar. So today I am going to talk about the relation between number theory and graph theory. Using some number theory concepts, I am going to derive some graphs. From these number theory concepts, we can derive so many graphs. So in this lecture, we are going to see some derived graphs from one or two number theoretic functions. Okay. So have you seen the screen, sir?
Yes, sir. Yes.
Yes.
Now you are seeing your entire screen. Kindly share the PowerPoint, sir, please.
Yes. So have you seen this PowerPoint, sir? So
Not yet, sir. Not yet, sir.
the PowerPoint is not visible, huh?
Ah, yes, sir. Yes, sir.
So wait a minute, it is loading, sir.
Okay, sir. Okay. Dear participants, please be wait since our resource person had a technical issue, network issue. So now he has rejoined. Sir, is it okay now, sir? Are you able to share the screen? Yes, sir. And now we can see your screen. Kindly unmute yourself. Yes, sir. Kindly unmute yourself. We are not. We couldn't hear your voice. So unmute yourself. Click the mic symbol in the Google Meet. கீழே கார்னர்ல அந்த லெஃப்ட் கார்னர்ல இருக்கு பாருங்க. Yes, browser, please.
Yes. Okay. So is the screen visible?
Yes, yes, it is visible.
So okay.
Yes, browser. Yes, browser.
So we'll start the lecture. There is a relation between number theory and graph theory. Number theory is mainly focused on integers. It covers topics ranging from divisibility of integers to modular arithmetic and linear congruences. Graph theory is more focused on graphs that are used to represent things such as the linking of web pages, the shortest distance, mostly used in GPS and networks, etc. Both number theory and graph theory are part of what is called discrete mathematics. Number theory, like many other branches of mathematics, is often concerned with sequences of real or complex numbers. In number theory, such sequences are called arithmetical functions. A real or complex valued function defined on the positive integers is called arithmetical function or a number theoretic function. Several number theoretic functions which play an important role in the study of divisibility properties of integers and the distribution of primes. So there are so many number theoretic functions. Some of them are Euler torsion function, Mobius function, manifold function, Realis's function, divisor functions, etc. In this lecture, it is derived the graphs from some number theoretic functions such as Euler torsion function and divisor function. And also, I am going to derive the graphs from the concept of quadratic residues. It is also studied some properties of these graphs. First, we are going to see the Euler function graphs. Next, the divisor function graphs. Next, quadratic residues graphs. Next, some references. So first, we are going to see what is meant by Euler function graphs. Before that, first we will know what is meant by Euler function. Some of you know what is meant by Euler function. The Euler function is defined as follows. The number pi of n is the number of positive integers less than or equal to n that are relatively prime or co-prime to n. This function is called Euler's function, Euler's pi function. Sometimes it is called the torsion function. For example, you take the number 1. The numbers co-prime to 1 is 1. Therefore, pi of n is 1. Similarly, for 2, you take the prime number 5. The numbers co-prime to 5 are the previous numbers to 5. They are 1, 2, 3, 4. Therefore, pi of n is equal to 4. Similarly, for the other numbers. This is the definition of Euler function and the exams. I think all of you clear the Euler function definition. From this Euler function, we are going to derive Euler function graphs. Before that, we will see some properties of Euler function. We know that any integer n can be written as the product of prime powers. For example, you take 15, it is equal to 3 into 5. 3 and 5 are primes. You take 16, that is equal to 4 square. So any number can be written as the product of prime powers. It can be represented in the form n equal to p1 power a1, p2 power a2, etc., pk power ak, where p1, p2, etc., pk are distinct primes and ais are integer which are greater than or equal to 0. Suppose any integer is in the form, then pi of n, the formula for pi of n is equal to n into 1 minus 1 by p1 into 1 minus 1 by p2, etc., 1 minus 1 by pk. Also, pi of 1 is equal to 1. For example, you take 9, it is equal to 3 square. Then you apply the above formula. Pi of 9 is equal to 9 into 1 minus 1 by 3, that is equal to 6. Similarly, you take 15, which is equal to 3 into 5, then pi of 15 is equal to 15 into 1 minus 1 by 3. The 3 is the first prime, and into 1 minus 1 by 5, the 5 is the second prime. After simplifying, we get 8. So pi of 15 is equal to 8. By using this formula, we can find the number of primes, we can find the number of integers which are less than n and prime to n. Suppose if n is a prime, then pi, pi of n is equal to n minus 1. For example, you take any prime number p, the numbers relative to the prime number p is 1, 2, etc. p minus 1. So therefore, the total number is p minus 1. So if n is a prime number, then pi of n is equal to n minus 1. These two properties we are going to use in the Euler function graphs. So now we define a new graph. This is a new graph. Uh, it is defined by as follows. For any natural number n, the Euler function graph g of pi of n. The Euler function graph is denoted by g of pi of n. It is a simple VE graph such that the vertex set v of g of pi of n. It is the vertex set of the Euler function graph. It is equal to set of all a such that GCD of a n is equal to 1. That is a and n are relatively prime and a less than n. So the vertex set is the set of all numbers less than n and which are prime to co-prime to n. Then the edge set is E of g pi of n is equal to am, and GCD such that GCD am is equal to 1, where am belongs to V of g of pi of n. That is, you take any two numbers, any two vertices in V g of pi of n, you join the vertices if its GCD is 1. Then we will get some graph. That graph is called Euler function graph. So I will explain this graph by the following example. So here the Euler function graphs for n equal to 1 to 9 are given as follows. First you take n equal to 1. The vertex set is simply 1. The graph is just a singleton vertex. Next you take n equal to 2. The number of vertices relatively prime to 2 is only 1. Again we get a singleton vertex 1. So you take n equal to 3. The vertices O prime to the 3 is 1 and 2. Since 1 and 2 are relatively prime, you join them. So we get the graph G pi of 3. It is a K2. Complete graph on two vertices. Similarly, for g of pi of 4. So you take the prime number 5, n equal to 5. The numbers less than 5 and which are relatively prime to 5 are 1, 2, 3, 4. Here 1 and 2 are relatively prime, 1 and 3 are relatively prime, 1 and 4 are relatively prime, 3 and 4 are relatively prime. You join these vertices, we get this graph. If we take g pi of 8, you see that the numbers less than n and co-prime to n are 1, 3, 5, 7. Here 1 is relatively prime to 3, 5, 7. Similarly, for all other numbers, you join all the vertices, we get the graph K4. Then g of pi of 9, you take n equal to 9. You take the numbers less than n and co-prime to less than 9 and co-prime to 9 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 8. So you join the vertices if the vertices are relatively prime. We get that graph. So from these graphs, you observe that the number 1 is adjacent to all the vertices because 1 is relatively prime to all numbers. So in all the graphs, you can see that the number 1 is adjacent to all the vertices. We are going to use this remark to the proof of all the theorems in the Euler function graphs. Next, you note that the order of g of pi of n. The order of g of pi of n is the number of vertices is less than n and relatively prime to n. If you take any number n, the number of vertices is the number of indices less than n and co-prime to n. Already we have given the formula for the pi of n if n equal to p1 power a1 etc. pk power ak. But therefore, the order of g of pi of n is given by n into 1 minus 1 by p1 etc. 1 minus 1 by pk. If p is odd prime, the order of g of pi of p is exactly p minus 1. And also it is even. Since p is odd prime, then the order of g of pi of p is even if p is prime. Moreover, you see that the maximum degree for g of pi of n is given by delta is equal to n into 1 minus 1 by p1 etc. 1 minus 1 by pk minus 1 if n is a product of the prime powers, and p minus 2 if p is odd prime. Because you see that the vertex labeled by 1 is adjacent to all the vertices. For the vertex 1 has the maximum degree, which is equal to the, already we have given the formula pi of n, you subtract 1, we get the maximum degree. For similarly for the odd prime also. So next we will see some properties of the Euler function graphs. For any positive integer n, the Euler function graph g of pi of n is connected. So the proof is very easy. I am not going to prove anything. You just mention the proof. Clearly, 1 belongs to v of g of pi of n for any natural number n, and every integer is relatively prime to 1. Therefore, this means that the vertex 1 is adjacent to all the remaining other vertices in g of pi of n. Therefore, the Euler function graph is a connected graph. Next, the Euler function graph is not Eulerian. The graph is Euler function graph, but it is not Eulerian for any number n, because for any n greater than or equal to 3, pi of n is even. Already we know that pi of n is even, and therefore there are even number of vertices in g of pi of n. Also, the vertex 1 is adjacent to all other vertices. This implies that the degree of the vertex 1, is odd number, and hence we get the proof, because in the Euler graph we know that the degree of every vertex is even. But here, the degree of the vertex labeled by 1 is odd. Therefore, the graph, Eulerian function graph, is not Eulerian. The next important result is if every pair of vertices in g of pi of n are not relatively prime, then g of pi of n is a bipartite graph. It has also a proof. In many proofs of the theorem, we have used the remark the vertex 1 is adjacent to the remaining vertices. Next, the remark. The following are some observations in g of pi of n. So you see that again we mentioned that remark, the 1 is adjacent to all other vertices. For the singleton set 1 is a dominating set. This is a minimal dominating set. The domination number for g of pi of n is always 1. Next, we can derive the number of edges cannot exceed p minus 1 C2 or p minus 1 into p minus 2 by 2 for any prime. This is the maximum number of edges in G of pi of v which cannot be exceed p minus C2. So the next we are going to see what is meant by divisor function graphs. Before that, we are going to see what is meant by divisibility and the number of positive divisors function, and then we will see divisor function. Next, we will see the divisor functions graph. All of you know what is meant by divisibility. You know that an integer a divides b, or b is divisible by an integer a, not 0, if there is an integer k such that b equal to ka, and we write a divides b. In case b is not divisible by a, we write a does not divide b. For example, you take the number 6, the divisors of 6 are 1, 2, 3, 6. Next, you take the prime number 7, the only divisors are 1 and 7. Next, we will see the definition of the number of positive divisors of the integer. The function tau of n gives the number of positive divisors of n, including n itself. For example, the divisors of 12 are 1, 2, 3, 4, 6, and 12. Therefore, tau of 12 is equal to 6. Also, we see that the divisors of 25 are 1, 5, and 25. Tau of 25 is equal to 3. Next, you take the prime number 17. The only divisors are 1 and 17. Therefore, tau of 17 is equal to 2. Next, we will see the some formula for regarding the number of divisors of the positive integer en. As usual, any integer can be represented as the product of prime powers. If n equal to p1 power a1 etc. pk power ak, then tau of n is equal to 1 plus a1 into 1 plus a2 etc. 1 plus ak, where a1, a2 etc. ak are the powers of the distinct primes. Suppose it is a prime, then tau of n equal to 2. Already know the divisors of the prime number are 1 and the number itself. Therefore, tau of n is equal to 2 n. If it is a composite number, we have the formula 1 plus a1 etc. 1 plus ak. For example, you take n equal to 24. 24 can be written as 2 power 3 into 3. Then tau of 24 is equal to 1 plus 3 into 1 plus 1. The powers are 3 and 1. 1 plus 3 into 1 plus 1, which is equal to 8. So if we take n equal to 11, then tau of 11 is equal to 2. So next we will see the definition of divisor function, which is already in the number theory. The divisor function d of n is defined by d of n is equal to set of all d such that d divides n is any positive integer. That means that the divisor function is the set of all divisors of n. That's all. Set of all divisors of n. For example, you take n equal to 2. The divisors of 12 are 1, 2, 3, 4, 6, 12. Therefore, d of 12 is equal to this set. So the divisor function is a set. If n equal to 7, which is a prime, then d of 7 is equal to 1, 7. But we are using this concept. We are going to define a newer graph, which is called graph of divisor function or divisor function graphs. So you take any positive integer n greater than or equal to 1, which has r divisors d1, d2, etc. dr. The graph of divisor function d of n is a graph it is denoted by G suffix D of n with the vertex set D1, D2, etc. dr. That the vertex set is the divisors of n. You note that the vertex set of the divisor function graph is the set of all divisors of n. The edge set is divided by such that the two vertices di and dj are adjacent if and only if either di divides dj or dj divides di for I not equal to j. So you join the two vertices in the vertex set such that if one is divides other or other is divides previous, then we get the new graph. That graph is called divisor function graph. I will explain this definition by the following examples. So you see, the divisor function graph for n equal to 1 to 10 are given below. As usual, you take n equal to 1. The divisor is 1 itself, therefore it is a singleton vertex. You take n equal to 2. The divisors of 2 are 1 and 2, and 1 divides 2. So we get the graph K2. Similarly for n equal to 3, which is K2. If you take n equal to 4, the divisors of 4 are 1, 2, 4. There are 3 vertices in G of D4. Here 2 divides 4, 1 divides 2, 1 divides 4. Therefore you join all the vertices, we get the graph K3. You take n equal to 5. 5 is a prime number. It has only 2 divisors, 1 and 5. 1 divides 5, we get G of T of 5 is K2. Similarly, we get for the graphs n equal to 6, 7, 8, 9, 10, etc. So here you note that if n is a prime, we get the n is a prime, the divisor function graph is just K2. So for you could take n equal to 3, for n equal to 5, for n equal to 7, we see that the divisor function graphs are only K2. Also, you note that in number theory, you know that the number 1 divides all the numbers, but therefore the vertex labeled by 1 is adjacent to all other vertices. In the Euler function also, we have seen that 1 is relatively prime to all other numbers and 1 is adjacent to all vertices. Similarly here, 1 divides all the numbers, therefore 1 is adjacent to all other vertices. So you know that for any g d of n, this is a divisor function graph on the integer n, the minimum degree delta and the maximum degree capital delta is equal to 1 when n is a prime. Already we see that n is a prime, the graph is just K2. The K2 has the minimum degree is 1 and the maximum degree is 1. Otherwise, if n is a product of prime powers, then the minimum degree is greater than or equal to 2. There is no formula for that. And the maximum degree is 1 plus a1 into 1 plus a2, etc. 1 plus ak minus 1, where a1, a2, etc. ak are the powers of the prime factors of n. Next, the result is for any positive integer n, the divisor function graph g d of n is connected. The proof is same as in the Euler function graph. Here, the vertex 1 is adjacent to all the vertices. Therefore, obviously, we see that the graph g d of n is connected graph. The next result. For any positive integer n, it is not a prime, the divisor function graph g d of n has at least one cycle of length 3. So in this graph, we have at least one cycle which has the length 3. It is very obvious. Here, it is given that n is not a prime, then there is at least one proper divisor d of n such that d is adjacent to with 1 and n. So n is not a prime, so we get at least one proper divisor d of n such that d is adjacent to with 1 and n in g d of n. Hence, we have the cycle from 1, the divisor d, and the n, and again it 1. We get the cycle whose length is 3. So in any graph g d of n, we get the cycle of length 3. The next result is for any positive integer n, the divisor function graph g d of n is a complete graph if and only if no two proper divisors in d of n are relatively prime. So this is another result. It gives a lengthy proof. So we'll move the next result. For any positive integer n, the divisor function graph g d of p power n is complete. Suppose n is a prime power, just one prime power, then the corresponding divisor function graph is a complete graph. Next, the divisor function graph is a n regular graph. If the given number is prime power, then the graph is a n regular graph, which is depending upon the power of the prime. Next, the planar property. The characterization for the divisor function graph is planar if every vertex of g d of n has a degree, at most degree 4. Next, these are the statements. They are equivalent as far as the divisor function graphs. For any composite number n, the following statements are equivalent. G d of n is a block. Already you know that what is meant by block. Block is it has no cut vertex. Any two vertices of g d of n lie in a common cycle. Next, any vertex and an edge lie in a common cycle. Any two edges of g d of n lie on a common cycle. These four statements are equivalent for a composite number n. Next, for any positive integer n, the divisor function graph g d of n square is an Euler graph. So if you take any number in perfect square, for that number n square, we construct the divisor function graph. We always see that it is a Euler graph. But in the Euler function graph, that graph is not Euler, but here for this particular number n square, the divisor function graph is an Euler graph. Next result, for any prime p, the divisor function graph g d of e is a tree with one edge. So already we have seen that this property. For any prime p, we have the only the two divisors, 1 and p. If 1 divides p, you join the two vertices, we get the resulting graph is K2. So K2 is a tree which has one edge. Next, if n is prime, then g d of n is two colorable. This is a colorability property of divisor function graph. The proof of this result is very obvious. Since n is prime, its divisors are 1 and n itself. Hence, g of dn has unique edge. Already know that this corresponding graph is K2. The colorability of K2, it is two colorable graph. And it is obviously we see that the complete graph K2 is two colorable. Therefore, if n is a prime, then GT of n is two colorable. Next, we some observations in GD of n. For a prime P, GD of P is the only triangle-free graph. So you see the example. You take the prime number. For example, you take n equal to 5. The corresponding graph is K2. It has no triangle. That is an obvious result. Next, adjacency and incidency matrix of divisor function graph G of n can be defined, and its properties are analogous to a simple graph G. The properties are same in the graph ordinary simple graph G and the divisor function graph G of n. So thus we have seen that the two new type of graphs which is derived from the number theoretic functions, the Euler-Thomson function and the divisor functions. These two are number theoretic functions or arithmetic functions. From this we get derived a newer graph and we have seen some of its properties. Next we are going to see what is meant by quadratic residues graphs. So it is not from the number theoretic function. It is from the concept of number theory. So already some PG students know that quadratic residues. From the quadratic residues concept, we derive a new graph. That graph is called quadratic residues graph. So first we will see what is meant by quadratic residue. We always say that simply, we always say that simply a quadratic residue modulo m, not quadratic residue. You always said quadratic residue modulo m. You add what is the modulo number. Okay. The first we will see the quadratic residue modulo m. For all a such that a GCD of a m is equal to 1, a is called a quadratic residue modulo m if the congruence x square is congruent to a mod m has a solution. If this congruence has a solution, then we say that a is quadratic residue modulo m. If it has no solution, then a is called a quadratic non-residue modulo m. This is the definition of quadratic residue modulo m. We will see one example. We will see the quadratic residue of modulo 5. So the elements in 1, 2, 3, 4 are which are relatively prime to 5, and we will compute the squares mod 5. First you take x equal to 1, 2, 3, 4. X square mod 5 means first you take x equal to 1, you square it, it is again 1. You apply mod 5, the remainder is 1. Therefore, x square mod 5 is 5. Similarly for 2, if you take 3, the square is 9. Apply mod 5, the remainder is 4. Next you take x equal to 4, the square is 16. Apply mod 5, the remainder is 1. So x square mod 5 for 1, 2, 3, 4 are 1, 4, 4, 1 respectively. Therefore, the quadratic residues are the squares 1 and 4. You see the second row of the table, we have the numbers 1 and 4 only. Therefore, the quadratic residues are 1 and 4. And the remaining numbers 2 and 3 are quadratic non-residues. So next we will see the definition for reduced residue system, modulo m. You say reduced residue system, modulo m. So a subset R of the integers is called a reduced residue system modulo n if the first condition is GCD of Rn is equal to 1 for each R in n. So the elements of in R is relatively prime to n. This is the first condition. Next, the set R contains pi of n elements. Next, the third condition is no two elements of R are congruent to modulo n. No two elements of R are congruent to modulo n. If the set R satisfies these three conditions, we say that the set is reduced residue system modulo n. For example, you take the modulo 12. The reduced residue system modulo 12 is 1, 5, 7, 11. You see that 1, 5, 7, 11 are relatively prime to 12. 1 is relatively prime to 12. 7, 5, 11 are relatively prime to 12. The second condition is it contains 4 elements. Pi of 12 is equal to 4. Next, the third condition is no two elements are congruent to modulo n. You take any two numbers in this set. For example, you take 5 and 7. You see that 5 is not congruent to 7 modulo 12. Because 5 is congruent to 7 means its remainder is 12, which is not divisible by 12. Okay. You take 7 and 11. 7 is not congruent to 11 mod 12 because 11 minus 7 is 4, which is not divisible by 12. For the reduced residue system, modulo 12 is 1, 5, 7, 4. For using these concepts, we are going to define a new graph, which is called quadratic residues graphs. You will see the definition carefully. Let n greater than or equal to 2 be a fixed positive integer. We call a simple graph is a quadratic residue graph modulo n if its vertex set is reduced residue system mod n. So first you understand that the vertex set is just the reduced residue system mod n, such that the edge set is defined as follows, such that the two distinct vertices A and B are adjacent, provided that A square is congruent to B square mod n. Already in the reduced system, we have the condition A is not congruent to B mod n. A is not congruent to B mod n. Suppose if A square is congruent to B square mod n, you join the vertices A and B, where A, B belongs to the vertex set. Okay. This is the vertex set and this is the edge set. You see the graph is denoted by theta n, the quadratic residue graph modulo n. Okay. So you see in the mathematical form, V of theta n is equal to set of all A belongs to Z, the integers. The GCD of A and n is equal to 1 and A less than n. Next, edge set is set of all A, B such that A, B belongs to V of G and A square is congruent to B square mod n. If this condition is satisfied, we can join the two vertices. If we take any integer n, applying these conditions, we get a new graph. That graph is a quadratic residue graph. We will explain this graph by the following example. You take n equal to 7. So V of theta 7 is equal to 1, 2, 3, 4, 5, 6, which are relatively prime to 7. That pi of 7 equal to 6. The reduced residue system condition is satisfied. And you see E theta 7 is equal to 1, 6. 1, 6 means 1 is joined to 6, 2 is joined to 5, 3 is joined to 4. So how to construct this graph? You take the vertex at 1, 2, 3, 4, 5, 6. You plot the vertices 1, 2, 3, 4, 5, 6. So you see that 1 square is congruent to 6 square. That is 6 square is 36 is congruent to 1 means 35, which is divisible by 7. So you join 1 and 6. Similarly, 5 square is congruent to 2 square. That is 25 is congruent to 4. That is equal to 21, which is divisible by 7. You join 2 and 5. Similarly, you join 3 and 4. So you cannot join 2 and 3 because 2 square is equal to 4, 3 square equal to 9. So 9 is not congruent to 4 mod 7. So therefore we cannot join 2 and 3. Similarly, we cannot join 1 and 2, 1 and 4, 1 and 5, 3 and 5, 3 and 6, etc. So we get for n equal to 7, the quadratic residue graph is the disjoint union of complete graph K2. We have 3 disjoint union of K2s. So we take n equal to 16. The vertex set is 1, 3, 5, 7, etc. 15, which are relatively prime to 16. And E of theta 16 is equal to 1, 7, 1, 9, etc. 11, 13. So you plot the vertices 1, 3, 5, 7, etc. 15. So you join the vertices applying the condition a square is congruent to b square mod 16. For example, 1 square is congruent to 9 square. 9 square is equal to 81. So we subtract 1, 80, which is divisible by 6. So I join 1 and 9. Similarly, I join 3 and 13, 11 and 5, etc. But I am not joining 3 and 7 because 3 square is not congruent to 7 square mod 16. So I am not joining 3 and 7. Similarly, we are not joining 3 and 15, 3 and 9, 11 and 1, 13 and 7, 13 and 9, etc. So here we see that theta 16 is a quadratic residue graph, which is disjoint union of two complete graphs K4. Next, you take n equal to 24. You construct the vertex set. From the vertex set, you applying the condition for the quadratic residue graphs, we get the edge set. The corresponding graph is as follows. This graph is complete graph on 9 vertices. So from these examples, we clear about the quadratic residue graphs. So you know how to construct the quadratic residue graphs for a given number n. Okay. Next, we will see some properties of quadratic residue graphs. For the properties, we are using the number theory result in the congruences. In congruences case, so many results. Using these results, we can construct some quadratic residue graphs. So these results are already in number theory, in congruence theory. The congruences x square is congruent to a mod 2 power e, where e is an integer, e greater than or equal to 3, as either no solutions or exactly 4 incongruent solutions. Next, I have mentioned 3 results A, B, C, which are also used to prove the following theorems. So I'm not going to prove any theorems. I just mentioned the results in number theory, applying these results in proving the various results for quadratic residue graphs. Let theta n be a quadratic residue graph. If n equal to 2, theta n is empty graph. It is obvious. If n equal to 2 square, that is equal to 4, the divisors are the n equal to 4. The reduced residue system for 4 is 1 and 3. Applying the quadratic residue graph conditions, we get the graph K2. It has only one edge. Next, if n equal to 2 power r, where r greater than or equal to 3 is any integer, then theta n is equal to 2 power r minus 3, not k, r minus 3 k4. That is, theta n is disjoint union of 2 power r minus 3 graphs. That graphs are k4. We are using the above results, above number 3 results. We can prove that theta n is equal to 2 power r minus 3 k4. If n is an odd prime, then theta n is equal to n minus 1 by 2 k2. The n minus 1 by 2 disjoint union of complete graphs k2. If n equal to prime power, p power r, where p is an odd prime and r is any positive integer, then theta n is equal to p power r minus 1 into p minus 1 by 2 k2. This is also the disjoint union of complete graphs k2. This is the proof. We are using the number theory concepts. Next, in general, any number can be represented as the product of prime powers. Then the quadratic density graph theta n is equal to pi of n by 2 power m k 2 power n. Again, pi of n by 2 power n is a number. This theta n is a disjoint union of pi of n by 2 power n graphs k 2 power m. This is the proof. We are using the congruence theory. Next, take the more general form, including the even prime too. N equal to 2 power r, p1 power alpha 1, etc. pm power alpha n. Pi's are distinct odd primes, and alpha I and r are positive integers. Then theta n is equal to this of the form. If r equal to 0 or 1, pi of n pi 2 power n k 2 power n. If r equal to 2, theta n is equal to pi of n by 2 power m plus 1 k 2 power m plus 1. If r greater than or equal to 3, then the quadratic density graph theta n is pi of n by 2 power m plus 2 k 2 power m plus 2. This is the proof. Next, this is the characterization for quadratic density graph should be complete graph. Theta n is a complete graph kn if and only if n is a divisor of 24. If n is a divisor of 24, the quadratic residue graph should be complete graph kn. So this is the proof for that. So overall, we see that the quadratic residue graph theta n is either a complete graph or disjoint union of complete graphs. There is no other graphs. The quadratic residue gives only the graph either complete or disjoint union of complete graphs. So we are using the number theory concepts in quadratic residues. We have derived the new graph, quadratic residue graphs, and the final result is it is either complete graph or disjoint union of complete graphs. So thus we have seen that from the number theoretic functions, the two functions, Euler-Thomson functions and Divisor functions, we derived new graphs and their properties. So many there are properties, so many other properties are there. Now you have to study from the references. The quadratic density graphs, I think it is exhausted because it is completed up to the last remark. It is either complete graph or disjoint union of complete graphs. So these are all my references from number theory books and graph theory books and the papers from quadratic residue graphs, divisor function graph, and Euler function graphs. So thank you very much for listening my lecture. Thank you one and all.
Thank you, sir.
Thank you.
Participants, do you have any? Participants, if you have any questions, please do post them in the chat box.
So, any questions?
Sir, I have one question, sir. May I ask?
Yes.
Sir, have people ever considered about the complement of these graphs, Euler graph, Euler
Yes.
function graph? Does that have any specific beautiful property? Is it studied, sir?
Yes, sir.
The complementary graphs of Euler function graph, divisor function graphs. Also
Complementary graphs.
graphs, complement graphs.
Complement of a graph. Huh?
Yes, yes, sir.
Complement of a graph. Yes. So I'm not.
Okay,
I'm
okay.
not studying that. We will see.
All right, sir.
So you take the complement of Euler function graph. What is the resulting graph? You ask
Yes,
me
sir,
the
yes.
question. Okay. Huh?
Yes, sir. Does it have any beauty? I'm asking. So,
I think it has some beauty, but I'm not right.
okay, sir.
We will try, madam.
Thank you, sir.
Thank you, madam. So, any other questions?
Yes, you can ask the question. Nina.
So, you ask the questions.
Meena ma'am, you can ask the question yourself.
So, you raised the hand.
Meena ma'am. Sir, okay. If she's not having a question, sir, I have a question.
Yes, sir.
Sir, shall we using the same concepts for chemical graphs?
Same concept to chemical graphs.
Yes, Euler function.
In which sense?
Sir, nowadays chemical graph theory is an emerging one.
Yes.
They were using the graphene and the other chemicals. They have represented the chemicals as in terms of graphs. So since for every graphs we are using this quadratic residue concepts or Euler Euler function
Okay.
to the graphs. Can we use it, sir? Because since every chemical form has a graphical representation, shall we use it, sir?
So, if the chemical representation of the chemical graph is an Euler function graph, we can use the properties of Euler function graph. So, if a chemical graph is a Euler function graph, we can use the properties of Euler function graph. Otherwise, I think we cannot use. But chemical graphs are the energy of graphs is applied to chemical graphs. But I don't think about the Euler function graph. Suppose,
Okay, sir.
yeah, suppose if any of the organic compound has the structure as in Euler function graph or division function graph, using that properties, we can study the molecular structure of the graphs. Otherwise, I don't know about that.
Okay, sir. Okay, sir. Okay.
Thank you.
Sir,
Thank you.
what is the scope of these topics in the applications of graph theory, sir?
See, these two derived graphs are also application because
Yes.
we are applying the graph theory to the number theory concepts. In real life problem, we have to see, sir. Suppose the Euler function graph and the divisor functions are applied in some real life problems. We are using these graphs also to that real life problems. definitely I got that idea.
Okay, sir. Could you please tell me about how you can get the ideas that to mingle the number theory and the complex analysis concepts with graph theory, sir? Since there are more budding researchers in the YouTube live link.
Yes. You are relating the number theory and the graph theory, okay?
Yes, sir. Yes, sir.
So if there is a relation in numbers, we can easily apply that relation to graph theory. For example, relatively prime. Relative prime. These are the relative prime concept is a relation between two numbers. Okay, V A and V are relatively prime. The GCD is one. This is one relation. Another, the divisibility is also another relation. If you take any two numbers, either one divides another number or this number divides that number. Otherwise, it won't divide. So you will get two possibilities. In relatively prime, you have two possibilities. One is relatively prime or it is not relatively prime. In divisibility also, you have two possibilities. One, it is divisible. Another is it not divisible. If we got the two relations, we can combine these two relations in graph theory. We can construct new graphs or new labelings. In decomposition also, we can use these concepts. I have used the divisibility and the relative prime concepts in decomposition, energy, and labeling. In similar way, we can try using these concepts to other fields of graph theory, I think.
Okay, sir. Thank you so much, sir. Thank you. So, Safina ma'am,
Yes, sir.
yes. Now I invite you to give the vote of thanks, please.
Yes. It is my privilege to propose the vote of thanks. On behalf of everyone, I extend a hearty vote of thanks to our most valued resource person, Dr. K. Nagarajan, for sparing time amidst his busy schedule to enlighten us with his talk. Today, you showed us the relations between number theory and graph theory. We learned Euler function graphs, divisor function graphs derived from number theory functions, and also quadratic residue graphs. Thank you, sir, for showing us how one field of mathematics can be related to another field. I, I am very thankful to the participants and all the members who are responsible for the successful conduct of today's program. Thank you, one and all. Thank you.
Thank you very much, madam.
Thank you, sir.
So once again, thank you, dear resource person, for your wonderful and uh, simple speech. You have simplified the concepts to us. Thank you. And thank you, dear participants. We'll meet you tomorrow by 3 o'clock on the sixth day of this faculty development program. Thank you all. Thank you. Have
Thank
a
you.
nice day.
Thank you, sir.